Hello, everyone. Welcome to this new Latin American webinar of physics. My name is Walter Tangarife. I work at Loyola University, Chicago. And it is my pleasure today to introduce our speaker. Today is Mitrajyoti Ghosh, or Millo, who will talk about what happens when muonium becomes antimuonium, if this is a possible new window into new physics. Millo got his PhD at Cornell University, and right now he's a postdoctoral scholar at Florida State University. Thank you for sharing your work with us, Millo. We're very excited about your talk. For all those who are watching right now on YouTube, remember that you can ask questions via the chat on YouTube. And they will be happy to read those questions to Millo at the end of his talk. And then remember that you can always subscribe to the YouTube channel or through our social network so that you are always updated on any upcoming talk. All right, so thank you, Millo, for being with us, and you can take it away.
Thank you so much, Walter, for inviting me to this seminar. So let me share my screen. Okay, it's visible, right? You can see me. You can see my screen. So
yes.
All right. So today I'll talk about muonium and its conjugate particle antimuonium. It's something that I've been working on for the last year, and it's something that I'm very excited about. So let's get on with it. So my primary motivation for working on muonium and antimuonium is neutrinos, because as we all know, the standard model neutrinos, they are massless, but that's not the full story, because real neutrinos, they are massive and they are not explained by the standard model. So we have neutrino oscillation experiments that tell us the mass square differences, but we so far have no idea what the absolute masses are. So that's a mystery of nature that we haven't solved yet. Um, uh, that's just the first mystery. The second one, which I personally am very excited about, is are neutrinos their own antiparticle? In other words, are they Dirac particles or are they Majorana particles? So this is also something that we don't know anything about, and muonium antimuonium mixing, as I will tell you, has something to say about this. And thirdly is a question that is quite popular these days, which is there CP violation in the leptonic sector? So we know that there is CP violation in the quark sector through the CKM matrix. In the leptonic sector, we also have the lepton mixing matrix called the PMNS matrix, which I have here on the screen. And the question is, does it have a CP violating phase? That's one of the questions. Once again, if there is another question too, which is that if neutrinos are Majorana, then this matrix can also have two additional Majorana phases, and we will see if muonium antimuonium mixing has something to say about that. All right, so at this point, I think it's very well known that neutrinos are extremely hard to catch. So there are millions of neutrinos are going through you right now. So what's the best strategy? Of course, since they're so hard to detect, how about thinking about indirect detection? Just don't catch them, try to see them through some other means. And in fact, Walter and I, we have a few papers on this. We collaborated a while ago, and we have this series of works on neutrino mediated forces, where like neutrinos mediate forces between fermions as long as they're weakly charged. And this force is fascinating. It's very weak, but it's still fascinating. And we have some work on this, which you can look at. But that's not the subject of today's talk. So in today's talk, I'll not go into this. I'll talk about muonium and antimuonium. So let me introduce you to false muonium and antimuonium. Why false? Because, positronium is E plus E minus, toponium is T plus T minus, but muonium is not mu plus mu minus. So here's true muonium at the corner, very unhappy. But real or muonium, what we know, in the literature is false muonium. It's a bound state of mu plus and E minus. And it is in fact the simplest hydrogenic bound state. It is even simpler than hydrogen. Why is it simpler than hydrogen? Because in hydrogen you have to worry about the proton. The proton has it's a very complex system. There are plenty of annoying QCD going on there. But the muon and the electron, they're fundamental particles. So you don't have to worry about all that QCD. So this is pure QED bound state, and that's why it's very easy to analyze. However, the only big problem is that muonium is not forever, which means that muonium decays, and it decays pretty fast. As you know, this Feynman diagram is something that you do in your QFT classes right in the beginning. And most of you have calculated this, and you know that the decay time for the mu plus is like 2.2 microseconds. So that's not very high. So if you have muonium, you can't keep looking at it forever like you can do hydrogen. But no matter, let's see what we can go with this. There are plenty of things you can do with muonium. You can do spectroscopy, and people do it all the time. But for the purposes of this talk, I'm going to focus myself on muonium antimuonium mixing, which is essentially what I'm trying to show here. Nice thing about it is it's lepton flavor violating, which is that, it does not, so muonium becomes antimuonium, meaning that the mu plus becomes a mu minus and E minus becomes an E plus, which violates lepton flavor. So you don't expect to see this in the standard model. This has been discussed long back in the 1960s by, none other than Weinberg. And he primarily viewed it as a way to look at new physics beyond the standard model. So on these diagrams here, there are a bunch of models that people have written in the past to probe muonium antimuonium mixing. I don't know enough about all of these models, but they have been done, and there are effective field theory treatments of muonium where they write down this operator here and they try to analyze its Wilson coefficients and probe new physics. But today we are worried about neutrinos. And when neutrinos are massive, the standard model is no longer lepton flavor preserving. So you can have these diagrams when neutrinos are massive. And look, these diagrams are when muonium becomes antimuonium. So you start off as muonium and you can become antimuonium, not just because of new physics beyond the standard model, but also in the standard model because neutrinos are massive. So that's interesting because it's not really a topic of conversation. Most people don't talk about this, and this is fun. So why not? I will present now the outline for my talk. So I have two parts. So the first part is I will discuss some of the theory behind, basically some calculations. Don't worry, I won't bore you with all the details. But so I will talk about muonium antimuonium mixing in different scenarios. I briefly hinted that there is a difference between Dirac and Majorana, and when neutrinos are Dirac and Majorana. So I will talk about that and some other cases. And then I will move from there to some experimental aspects of looking at muonium antimuonium mixing. And we are currently working on a paper the results of which I will present here. The paper is about to come out very soon, so it's this October. So look out for this maybe in the next week or so. Okay, so let's go into the theory aspects of it. So I've heard a lot of people in the literature call this muonium antimuonium oscillation. So the first question that we should just get out of the way is this really oscillations? The eigenstates of the standard model Hamiltonian are not the flavor eigenstates because flavor is not a preserved quantum number. And so the mass eigenstates are what I have here on the left. So they have the two mass eigenstates of muonium and antimuonium have masses m1 and m2. And they also have decay rates gamma 1 and gamma 2 because muonium decays. However, for most intents and purposes, the difference between M1 and M2 is very, very small. So, the mass of muonium is essentially just the mass of the muon. Also, the decay rate of muonium is simply the decay rate of the muon. So it becomes important to see, so muonium and antimuonium, they oscillate with into each other with this frequency of 1 over this mass difference, right? And it's important to find out how does this time period compare with the decay time of muonium. So the decay width is very easy. We have this ancient formula in very low resolution to show how ancient it is. It's the muon lifetime, which muonium lifetime is essentially just the muon lifetime. There are corrections, and people have worked on this long back, but it's just the muon lifetime for the purposes of this talk. Whereas, so that's gamma, that's the decay width, and the oscillation frequency, which is delta m, is given by, it's a bit trickier because you have to calculate this amplitude of muonium becoming antimuonium through some physics over here, and take its real part and then divide by the mass of muonium, which is just mass of the muon. And I could have done this for you, but then I realized that, I just did it at the back of my, back of the envelope. And it turns out that if you actually calculate delta m and then find out what it means in terms of years for, for very optimistic purposes, this frequency time is 10 to the 9 years or so. So of course, for muonium to become antimuonium and back again, the time period is like 10 to the 9 years. So let's just forget about this. We know that muonium does not oscillate. It just basically decays. And it decays before a period is complete. So then what exactly am I talking about? If I just told you that muonium does not oscillate to antimuonium, what is it that I'm going to do? So this is what I'm interested in, something called a conversion probability, which is so if you look on the left, so there's muonium and it has certain decay products, okay? And then there is antimuonium, which has certain decay products, which I mean, so I've just color coded them so that, it's clear that they are actually different things. So the green and the purple, they are different states, CP conjugate states. So what I'm worried about, or what I care about, is if I start with muonium, I mean, it doesn't oscillate into antimuonium and back and forth, right? But what can happen is muonium just decays into antimuonium decay products, and that's called the conversion probability, which is PC. And essentially, the what it looks like to us is this diagram here, which is this muonium here decaying into the purple final states, which are the final states that are typically attributed to antimuonium. So once again, I will not bore you with the mathematical details of everything, but I mean, I'll just give you the formula. The conversion probability is given by this combination of mixing amplitudes on the right. So sigma 1, 2 is muonium becoming antimuonium. A Feynman diagram like this, for example. And sigma 2, 1 is the other way, which is antimuonium becoming muonium. You take them together, you multiply them, find its absolute value, and then you divide it by this mass and the width, and that gives you this probability. So I mean, we can talk later about how to derive this, but this is essentially what we want to calculate. So then let's just calculate, right? Remember, we care about neutrinos, so I'll give you the bad news first. Let's start with the case when neutrinos are Dirac. So then you have these Feynman diagrams, two Feynman diagrams. It's very reminiscent of KK bar mixing, and you can calculate them, you evaluate the loops and everything. These Feynman diagrams are in fact convergent. And when you calculate them and put in your formula for the conversion probability, you get something like this over here. I will explain where everything comes from. So starting with the most important piece, which is this me mu squared that appears in the numerator over here. And that is in fact given by this linear combination. How does that come up? Let's just go and look at one of the neutrino lines. You see that the PMNS matrix elements come from each vertex. But there is this m squared. Mi is one of the neutrino mass eigenstates. And there is this m squared. So where is that coming from? Well, I mean, we have very light neutrinos, and so we took this propagator. The typical momentum that's going through this propagator is roughly the mass of muons. So p is of the order of muon mass, and so we can expand this propagator in the light neutrino masses, and we get a few terms, right? So if you look at the first term very carefully, you'll see that it's just 1 over p squared. It has no I index, and if you put it back in this with the couplings, then this sum without the m, so just forget the m over here, is 0 because of unitarity. The PMNS matrix is unitary. So that's why this first term is not picked up at all. That vanishes. It's like the equivalent of the Jim mechanism, but for leptonic physics. So the leading order piece that you can get in the case when neutrinos are Dirac is this mi squared. And that is a problem because you pick up an mi squared from each neutrino propagator. That gives you 4 powers of neutrino mass, because 2 from each. Then you have to square it, and you get 8 powers of neutrino mass to get the probability. And so you reach this very abysmal number of 10 to minus 95, assuming some reasonable numbers for the neutrino masses here. So if you assume neutrinos are of the order of 0.1 eV, which is given by, that's the maximum they can be from constraints, then this Dirac number comes out to be 10 to minus 95. We don't have 10 to the 95 particles in the universe, so this is completely hopeless. And I also forgot, if someone wanted to know what this A0 comes from, it's important because this mu plus and E minus are part of a bound state. They are not free. So it's not enough to just calculate this diagram. You also have to include the boundedness of the mu plus E minus system. If you take care of that properly, you just basically sum over an infinite number of photons. Then it's nice that the Schrodinger equation pops out, and the Green's function just gives you the wave function, and the wave function has this Bohr radius dependence. So so this formula takes into account all the wave functions and the neutrino masses and everything, and it's just not very good because 10 to minus 95. Right. Majorana is a little bit better. The question is how better? And so we'll go over it together once again. In the case of Majorana neutrinos, there are all 4 of these diagrams they contribute. So the diagrams on the top are exactly the same as the Dirac ones. The diagrams on the bottom are the new Majorana diagrams, where you can see that this Majorana mass insertion in the neutrino legs will give you lepton flavor violation. So it violates lepton flavor by 2 units. And so where was I? Yeah. So the first 2 diagrams, as we saw in the previous, in the case of Dirac, is tiny because it's got like 8 powers of neutrinos or whatever, and so we can drop it. But these 2 diagrams in the bottom, the Majorana diagrams, they don't have that many powers of neutrinos, and we will explain that soon. So what comes in the second case is this combination MLL, which has only 1 power of mass. Sorry. Why is that? And the reason is, you look back to the neutrino lines once again. Each vertex, it picks up a UPMNS matrix element. However, because in each vertex your neutrino is being destroyed and a charged lepton is being created, you don't get a star for one of them. So you literally get the UPMNS matrix squared, and so they are unitary, but so there is no relationship for the squares of the UPMNS. So that's why in this case you don't get rid of the leading piece because of unitarity. However, you do pick up a mass mi because of this this mass insertion in the propagators. And so these diagrams, they pick up 1 factor of mi from each propagator. So each diagram, the amplitude has 2, and then the probability has 4, which is what you see in this formula over here. So that's already very good because it's 4 powers of neutrino in the probability as opposed to like 8, right? So what does that mean for our probability for muonium antimuonium mixing? Is that this formula comes out to be not as terrible. The number is 10 to minus 56 for probability, assuming some reasonable mass for neutrinos. But also, these diagrams are not convergent, and so we have to include a cutoff, which is basically the scale at which or the scale of new physics that gives the neutrinos a Majorana mass, right? So for example, we repeated this calculation for, type 1 seesaw, which is the simplest case. And in that case, this lambda is just replaced with the mass of the heavy neutrinos in type 1 seesaw. So yeah, so assuming that lambda is like 10 to 14 GeV, which is like a natural choice for it, the probability that we find for Majorana neutrinos is 10 to minus 56. Yeah, and the other thing is it depends on this linear combination M mu mu. Neutrinoless double beta decay depends only on MEE. So this feels like a complementary probe for M mu mu, because M mu mu, there are no other experiments that measure this combination M mu mu. So if you're trying to look at like other combinations of PMNS matrix elements, this seems to be, another avenue where you can look for it, right? So let's summarize what we found in the muonium antimuonium mixing score sheet. So Dirac did his best and got 10 to minus 95, and Majorana did his best and got 10 to minus 56. So this observable and muonium antimuonium mixing shows a 40 order of magnitude difference between Dirac neutrinos and Majorana neutrinos, which I thought was very interesting because usually finding an observable which distinguishes between Dirac and Majorana neutrinos is pretty difficult, but this seems like it's a very drastic difference. So yeah, but then we can also ask several questions based on this, right? So first of all, you might be very tempted to ask, has this not been done before? And I was very surprised as well that it was never done before. This is kind of a new calculation. No one did the Dirac case. I think it's because people thought, oh, it's small, so let's not worry about it. Also in the Majorana case, there is a previous calculation, but that kind of that was not right, because they confuse this system with the KK bar system, which is very different. The KK bar system, the strange quark and the down quark, they are in a bound state where the mass of the bound state is much larger than the strange and the down masses. Whereas in muonium, the bound state is QED, and so it's a very non-relativistic system. So the electron and the muon, they're quite slow. Whereas in kaons, you don't know. I mean, you can't even distinguish them as quarks anymore, right? So the calculation is very different, and this non-relativistic nature actually comes into the IR divergences of the loops that I showed before, and so you get different logs and a different answer if you do this, assuming it's exactly the same as a KK bar system. So we looked at previous calculations and we found that there was this mistake, and so we decided to do it properly. In the Majorana case, in the Dirac case, no one has done it before. Okay, so now let's ask more questions. We know that Majorana wins over Dirac now, but there are theories where you have both Majorana masses and Dirac masses, but the Majorana masses can be much smaller than the Dirac masses. That's not the usual seesaw regime. It's a different regime, and so the Lagrangian is kind of the same as seesaw, but then you have a condition that this M matrix over here, or I mean, this is elements of this matrix are much smaller than lambda times the VEV. So in such a situation, the neutrinos are called pseudo-Dirac, which is a bit weird because these neutrinos are not Dirac neutrinos. They're still Majorana, just called pseudo-Dirac because their Majorana masses are much smaller than the Dirac masses. So let's look at 3 generations. In that case, you can do all the diagonalization of the mass matrices, and that's just it's been done before. It's a very interesting exercise, but I will just give you the results of it. The spectrum for the theory that I showed in the previous slide is for 3 generations is 6 very light neutrinos. 3 of them are active, 3 of them are sterile, and there is a tiny, and they're quasi-degenerate, which is to say that, this M1 and M1 prime, they are very close to each other in mass. Similarly for M2 and M2 prime, and M3 and M3 prime. And so the mass differences are given by this formula. It's very simple, but this is the leading piece. There are higher order terms. The nice thing about it is that the solar neutrino oscillation data, it constrains this, this mass difference for the second generation by a lot. So it's very strongly constrained by this 10 to minus 11 EV squared number. M3 and M3 prime, I think, are also constrained by atmospheric neutrino data, but that's not as strong a constraint. So what happens in this case? Let's just go back to muonium antimuonium mixing. So the Majorana type diagrams that on the top ones, they go as this Majorana mass squared, whereas the Dirac type diagrams, they go as this Dirac type diagram to the fourth over mu squared, which is something that we saw previously at the amplitude level at least. So that means that the Majorana type diagrams can still win if this condition is satisfied, which is, I'm just comparing the two amplitudes, I know. And it's still, I mean, even with the pseudo Dirac condition, because of this MD over mu squared suppression, I think this condition can still be satisfied. So Majorana still wins in this case. But how big can it be? Is it still 40 orders of magnitude higher? So that's something we have to check. And in order to do that, we just went back to the drawing board, wrote down some operators in EFT that give you this kind of a pseudo Dirac situation, which is this dimension 5 operator does pretty well. And of course, the amplitude in the Majorana case is, the calculation is exactly the same, except now you have different Majorana masses, which are given by rotating away this new mass matrix by the PMNS a little bit. So yeah, so so this combination that we had in our previous answer is just replaced with a new combination of MLLs. And now there is a lot of algebra here that I did not wish to show, because what I did was, to take a look at the expressions and try to use the solar neutrino constraints to find out how big this MM can be, which is pretty easy to do, but it's just a lot of algebra, so I'm not doing it here. I'm just comparing the probabilities of the pseudo Dirac case with the Majorana case, and as I showed you before, it goes as m the Majorana mass to the fourth power, and you can constrain this using the solar neutrino data and a lot of algebra to be of the order of 10 to minus 11. So knowing that in the Majorana case, the probability is 10 to minus 55, and assuming normal ordering, in which case M3 is the largest neutrino mass that you can have. This number turns out, the pseudo Dirac conversion probability turns out to be 10 to minus 66 at max. That's already like 29 orders of magnitude bigger than Dirac. So it's not 40, but it's still quite big at 29. And you can repeat this calculation for the case when the neutrinos are inverted ordered, the mass ordering is inverted, and you don't get such a big enhancement, but you still get 21 orders of magnitude. So the key point is that pseudo Dirac is an enhancement over Dirac by like a lot. Does not make it very optimistic though, because it's still 10 to minus 66, which it's very hard to sort of see a number like that. Anyway, so let's go back and revisit our Dirac one last time, because the story is not, my story at least, is not complete. If you remember, what killed the Dirac neutrinos' chances at being successful in life, or at least being successful at converting muonium to antimuonium, is unitarity. Because as I explained before, he had to pick up this mi squared just because the PMNS matrix was unitary, and it could not do it with this first 1 over p squared term in the propagator. So then we thought, okay, if that's the case, what if we decided to make the PMNS matrix non-unitary using some sort of new operator, right? And there are ways you can do this. Basically, you just make a, there has to be a mismatch between the kinetic term and the mass term in the neutrinos. And you can do it there are several ways to do it. We just looked at one possible way, which is this dimension 6 operator. And with some, this is in the flavor basis, with some, coupling lambda alpha beta. You can, if you introduce this operator, then you can show that the PMNS matrix becomes different by this v squared over m squared times lambda piece. M squared is the scale at which, you have to, the new physics scale that you have to integrate out to get this operator. And so since UPMNS 0 is unitary, this new UPMNS is no longer unitary. So now you can go and calculate the Dirac diagrams again by inserting this new operator, which we did here in this diagram. And you can calculate muonium antimuonium mixing. But there is a small problem with that. So, small or big, depending on how you look at it. So the problem is that while you can do this, you can insert this operator in the Dirac diagrams twice and look for bar mixing. There is also the same physics that creates this operator could also potentially create a direct mu plus e minus to e plus mu minus vertex, which is shown on the right. And you can also do that the same thing by putting L6 twice and like a little bit and make a loop. So the issue is that by doing so, if the second diagram on the right here, if it becomes bigger than the first one, then we completely lose neutrino information because neutrino information was tiny anyway. And I think it's best explained through an example. So, for example, we considered two models, as in not did everything very thoroughly, but we were just trying to prove a point that you cannot do this. And the two models we considered was a Dirac singlet and a triplet scalar. So you can see the Lagrangians here. In both models, we can calculate this lambda alpha beta, which is in this dimension 6 operator. And in one case, it's just given for the heavy Dirac singlet, it's this product of the G's here. But in the heavy triplet scalar, this is much more complicated because it only happens at one loop. And so you need this loop factor, and you have to these Y's here are the Yukawa couplings of the charged leptons to the Higgs. So as you can see, it's different. And so if you try to compute the mixing amplitude using the two theories, you will get, for both of them, you will get an answer like this. However, the second piece here is important because the C and C prime, they come from different diagrams, like as I show here. In one case, with the heavy Dirac singlet, C prime and C are the same order of magnitude, which is just lambda squared over 16 pi squared. It comes from the loop. Whereas in the other case, C and C prime, they are very different. So, for example, on the right, you can see that there is a direct muonium antimuonium 4 Fermi operator. That's why it says G times G. And there is also this loop that you can calculate, which obviously is much smaller than the direct 4 Fermi contribution. So, I forgot to mention that the term on the left here is obviously subdominant to the term on the right because of this mw squared over m squared, which is small. So basically, this term on the right dominates the mixing amplitude. But as you can see in the heavy Dirac singlet case, you can still be sensitive to lambda e mu squared because both C and C prime are of the same order. Whereas in the heavy triplet scalar case, C and C prime are very different. So C is much smaller than C prime. So you will basically lose all lambda information, and you will only get that information on G if you assume this. So therefore, the point is that if by making the PMNS matrix non-unitary, we actually cannot say much about neutrino properties because it's very model dependent. Some models you can see neutrino properties come through this lambda e mu. In other models, you have no idea. So that's a key takeaway from trying to make PMNS non-unitary. All right, so that's kind of it for the theoretical exploration of MM-bar mixing. So what we have learned is that MM-bar conversion is in principle a good observable to distinguish between Dirac and Majorana, but of course the rates are really tiny, but there is a 40 order of magnitude difference between them. We saw that pseudo-Dirac neutrinos offer an enhancement in this conversion probability, but it's still very small. And then we also learned that adding unitarity violating operators may enhance mixing. It can, but we may lose out information on neutrino properties. And since we don't know, how nature wants to do this, so we have no idea how to say anything about neutrinos if we see unitarity violation. So then on the side, we also learned that the muonium antimuonium system is different from the kaon system, but that's a small point. If you're trying to actually calculate this, you may want to keep that in mind. Okay, so let's move on. And now that we're done with some of the theoretical things, let's talk about experiments. So yeah, we've been talking about what neutrinos and everything, but then how do you actually look for muonium antimuonium conversion? So the idea is very simple. You look for decays of muonium and antimuonium, and of course muonium decays. The traditional, the very easy weak decay of muons to electrons and neutrinos. So muonium has this is the biggest decay product or the decay product with the largest rate, and similarly for antimuonium. So what you can do is you can just detect the neutrino flavors and you will be done. You can see if it converted or not. But this is a joke slide. Don't believe me, because you cannot detect neutrino flavors. It's very hard to do. You can't even see the neutrinos. So all you are left with is basically the final state electron and positron. And if you remember, I told before in one of the slides that you produce muonium and you look for antimuonium decay products. So how it goes is you create an initial state that is just muonium. This one you can do because you just send muons through some material and it will capture electrons and it will give you muonium. And then you look at it decay. So if muonium decays, the positron that comes from the mu plus is going to be very energetic, right? Because it came from a mu plus decay. Meanwhile, the E minus was slow because it's an atomic electron. So it's not very fast, and so it's got energy of the order of the 13.6 eV or something. Meanwhile, it's the exact opposite for antimuonium. So, mu minus decays into a very fast E minus and a very slow E plus. So the way to detect conversion is in principle simple. You create an initial state that has muonium and you look for a final state where the electron is fast and the positron is slow. And I cannot tell you enough how many times I keep messing up the fast and slow. It gets a bit confusing even when you do it for a long time. So, but remember, the point is look for fast electron and slow positron after creating muonium. And so that's exactly what the experiments have tried to do. So there have been many experiments in the past, but the most recent experiment that has been completed is known as the MAX experiment. The MAX stands for muonium antimuonium conversion spectrometer. And I will go through the working of this experiment. But also, I like to let you know that this was done in 1999, and that's already like 26 years ago. So it's high time for an update. And so some people have already written a very long proposal for MACE, which is muonium antimuonium conversion experiment that they want to do in the future. So before I talk about Max and Mace, I'll just give you the brief schematic of how they work. So the signal is essentially, as I told you before, it's a fast electron, which has you send in a muon beam into a silicon oxide target where it captures electrons and becomes muonium. Then the muonium decays into it usually does not decay into a fast electron and a slow positron. But when it does, you set up, the slow positron is very slow. So you set up an electric field and a magnetic field to bend the positron into a positron, it's a calorimeter essentially, into a microchannel plate. And you also try to see the fast electron coming out of it. So essentially, you see the E plus and the E minus. You see the E minus through a tracker, so you can see its path. But the E plus, since it's very slow, it has to be accelerated through an electric field, and then a magnetic field bends it into this microchannel plate that detects the E plus. All right, so that's the idea of the experiment. Of course, there's like a lot of other things going on which I have not that much idea about, but a theorist's perspective is just this. So Max did exactly that. Max is the 1999 version. So Max looked at 10 to the 11 muonia. So that many, and then it found only one event that satisfied the criteria of an antimuonium decay event. So essentially one event where it was happy with how fast the electron was and how slow the positron was and things like that. And it didn't, based on the analysis with all the experimental backgrounds and everything, it decided that it was not signal. So I mean, it was statistically excluded, and so they put a background on the conversion probability they put a upper bound on the conversion probability of 10 to minus 11 or 10 to minus 10 if so that's 26 years ago. What Mace wants to do is they can upgrade the systems to look at more muonia. They have 3 orders of magnitude more muonia, and it also has methods to get rid of all of the previous backgrounds that Max was struggling with. So yeah, there's this paper talks about the proposal. It's a very long 100-page paper, but they're very thorough about what they want to do. However, for our purposes, the thing that I'm working on is understanding these backgrounds a little bit better. So I will talk to you about the backgrounds. The first few backgrounds that I will talk about are called the reducible backgrounds. So I think the name is pretty descriptive. What I mean by reducible backgrounds is that these backgrounds, you can actually do something to get rid of them. So the first one is called the internal conversion, which means that the muon decays into 2 positrons, 1 electron, and neutrinos. And this is even before it becomes muonium. So this can happen, and then if you somehow miss one of the positrons, if the other positron is very slow and the electron is fast, you might confuse this as a antimuonium decay event. So this is a background. I mean, it's not that it's rare, but still can happen, right? And the other thing that can happen is the positron can come out just like in a muonium decay without having become antimuonium. And then it can interact with some electron inside the detector, and then Baba scatter into making that electron fast, whereas this positron remains slow. And you could even confuse this as an antimuonium event. So these are the kinds of backgrounds that these experiments struggle with. And so what they can do and this Max did to some extent, and Mace has plans to do it. So you can reduce all of these backgrounds by being really selective with what kind of events that you want, and you can do that by selecting specific momenta. You can reconstruct the vertex at which point the decay happened. You can use time of flight requirements to make sure that you see the E plus and E minus exactly when you want to see them. And so my key idea is that you can get rid of these backgrounds if you work hard enough. So our experimentalist friends, they're very hardworking, and I think they can do a very good job at reducing these backgrounds by building a very nice experiment. However, the background that I am worried about is when the E plus and E minus that comes out from the muonium itself, they undergo scattering and they exchange their energies. So maybe muonium decays without becoming antimuonium, and then the E plus from muonium, which is supposed to be very fast, exchanges energy with the E minus from the same muonium, which is slow, and then fakes an antimuonium event. And in this case, you really don't. I mean, if in the case that you've exactly faked the momenta that you require, there is no way of knowing if where it came from, because the signal this coincides with the signal exactly. So this is something that I call an irreducible background. Okay, and so the Feynman diagram here on the top is what I call the irreducible background. So you see muonium, it converts to antimuonium, and then sorry, I'm very sorry. The numerator is the signal, the background is in the denominator. And I actually, this is a mistake. This muonium conversion should be in the denominator. So apologies for that. So I want you guys to focus on the denominator. Muonium converts into antimuonium, and then it undergoes this decay, but then there is Baba scattering over here, which makes it look exactly like an antimuonium decay, which is what is happening in the numerator. So I might have accidentally swapped the numerator and the denominator here, but I think, yeah, if there are any questions about this, I'm very happy to discuss after I finish the talk. So essentially the point is muonium, the background is when muonium decays and then does this, the electron and positron, they do a Baba swap. And this is what our paper is about, and it's coming out very soon. So stay tuned for that. Right. So our goal is to compute this signal to background ratio. That's what we want to do. And we have to remember that this signal to background ratio depends also on these cuts that I talked about, that they use to minimize the other backgrounds, right? So EF is the energy of the fast electron, and ES is the energy of the slow positron. So we choose cuts so that EF is between some number and mu/2, which is the maximum it can be. And we also choose cuts such that the slow electron is smaller than a certain, its energy is smaller than a certain maximum. So you see, I have normalized the EF and ES with respect to the energies that are typical. So for example, EF is usually its typical energy is the half of the muon mass, whereas ES, its typical energy is the Rydberg energy, or the atomic energy, 13.6 EVs, right? Okay, so we impose these cuts on the phase space, and then we can calculate this signal to background ratio that I told you about in the previous slide. And then we get this horrendous function. This calculation is, it's not so straightforward, and I don't want to bother you with the algebra, but we get a horrendous function that looks like this with I mean, I've defined everything here, but the key takeaway from all of this stuff is that this function of F's and S's, which stands for fast and slow respectively, this function is maximized at certain values of these cuts, and that maxima is 16. So the signal to background ratio is actually maximized to be about 10 to the 18 times PC, where PC is the conversion probability. Remember, the conversion probability will appear in the signal because muonium has to convert into antimuonium first. So this means that because of this limit on R, if your conversion probability is less than 10 to the minus 18, then your signal is going to be weaker than the background. And this is independent of the choice of any cuts you make. So that's actually pretty, it's interesting, but also kind of drastic, which means that, okay, I'll explain what it means after I show you this plot. So let's look at the significance of the signal. If let's say you want to probe a certain conversion probability, and you ask me how many muonia do I need in order to probe that conversion probability. So I have plotted that number as a function of the conversion probability here. And as you can see, for example, at 10 to minus 14, if you want to just look at a probability of 10 to minus 14, you need around 10 to 14 muonia. But beyond 10 to minus 18, this starts rising very sharply. So for example, to probe a probability of 10 to minus 20, you need 10 to 23 muonia. So it becomes worse and worse and worse, which means that if you want to go all the way down to 10 to minus 56 for Majorana neutrinos, which that's looks like it's completely impossible, right? The optimal cuts that we chose that minimize this number here are plotted here as a function of the conversion probability. So you can say, oh, these are the values I pick for my fast energy and my slow energy, so that I can do the experiment with the minimum number of muonia possible. But even if you choose these optimal cuts, as I show on the plot on the right, it doesn't change the number by that much. Okay, and what does it tell you? It tells you that this background is very irreducible. So I call it an irreducible background, and I think it's a funny thing to say. This irreducible background is truly very irreducible. Like, even choosing cuts very wisely does not help you that much. You will still struggle with the background at conversion probabilities below 10 to minus 18. So what it means for the experiments is that MACE is safe, because MACE wants to look at 10 to the 14 muonia, and it wants to probe probabilities around 10 to minus 14. So MACE lies around this area of the plot, and it's fine. So they actually never calculated this background, and they are all right in not doing this and completely neglecting it because it does not affect them. But any upgrades to MACE, which start looking at 10 to 17 or 10 to minus 18 probabilities, the signal is going to become overcome by the background, and you cannot neglect it anymore. And so that doesn't look very good for our Majorana neutrino levels of sensitivity. But I think it's interesting to find this number, and if you look at the number itself, it's kind of like it's only a function of QED stuff. So the find alpha, ME, and mu. So this is actually a very nice number to quote, that, oh, look, this is my limit on a muonium antimuonium decay experiment. So to conclude, the whole story of muonium and antimuonium is that, of course, you can do muonium antimuonium to look at new physics. And even then, you're kind of limited in how far you can go. If you go below 10 to minus 18, you have to be more careful. I'm not saying that you cannot see anything, because this is all about, these are very rare events, and you can maybe one of those events is a signal event, but you cannot be sure because the background is already bigger than the signal in that case. But yeah, so the Baba background is truly reducible, and you cannot choose cuts appropriately to reduce the number of muonia required to show that, oh, there's new physics at this level. right? So MACE is safe now, but then the future updates, they have to be very careful about how they analyze this. They can no longer ignore this background like they did with MACE. So that's essentially all that I had to say. So thank you very much for this opportunity. And yeah, thank you.
Right. Thank you, Millo, for the interesting talk. Now we are going to go to the question and answer section. So if there is anybody who has questions on YouTube, please write your questions on the chat of the channel, and then we will read the questions to Millo. While you do that, let's start with a question from anybody from here in the Zoom meeting. So Joel.
Thank you. Thank you very much for the talk. It was very, very nice. So I have many questions, but I'll start with one and then let the rest continue. So the first thing that comes to my mind is the comparison. I mean, the case of a neutrinoless double beta decay, right? In neutrinoless double beta decay, usually you say, oh yeah, the neutrinos are Majorana, and they can give you these predictions for neutrinoless double beta decay. However, then you say, okay, neutrinos have mass. We have to say why they have mass. So, for example, we can add heavy neutrinos. And the heavy neutrinos will give an additional contribution to neutrinoless double beta decay. Sometimes it can dominate the whole process. So my natural question here is if you have considered the possibility of using muonium antimuonium a transition to probe new physics models like heavy neutrinos, maybe lepton quarks or things like that.
Yeah. So that question is, there are people who have actually, there are papers that I've read which talk about heavy neutrino contributions to muonium antimuonium oscillations. So they exist. Yes, people have considered this. We were thinking about, oh, why did they completely neglect all the light ones? So we have, of course, there is a lot of literature on muonium antimuonium oscillations via heavy neutrinos. Yes, people have considered it.
So what are more or less the rates given by this process? Do you have them in mind?
I don't know them off the top of my head, but they essentially they have put some sort of what they try to do is they do heavy neutrinos, put heavy neutrinos in, and they kind of say, oh, this is the scale at which we have constrained them. I think that scale is at the TeV scale.
I see. But they can be probed by MACE. Like they can be improved by MACE, which is interesting because what you have calculated shows that standard model neutrinos, whether they are Dirac or Majorana, they are a negligible background to BSM searches using this.
Yes.
Super. Okay, thank you for this. I'll come back with another question later.
Thank you, Joel. Anybody else? Maybe I can read a question for you from the YouTube channel. I mean, it's a little bit more about semantics, but so Shantanu Desai says, at the beginning of the talk, you mentioned neutrino oscillation as evidence for physics beyond the standard model. However, the first papers on neutrino oscillations are from around 1957, predated Weinberg's 1967 paper on the standard model by 10 years. So is it really evidence for beyond standard model?
Oh, I mean, I guess it depends on whether you call neutrinos beyond standard model or standard model, right? Some people like to say massive neutrinos are beyond standard model. Some people say that they are standard model. Me personally, I like to say that massive neutrinos are not BSM. They are pretty much SM for me. Like, PMNS matrix and everything, they're part of the standard model for me. But a lot of people do say that it's beyond the standard model. For example, the Weinberg paper that talks about muonium antimuonium oscillation is they consider other things, of course, but I think they also mention massive neutrinos as beyond the standard model, even though it's already like 1960.
Right. Yeah. I guess yeah, it depends on what you call standard model.
Exactly.
If
So
you call the standard model Weinberg's theory of leptons, then yes. All right. Any other questions from here? Millo, I have a question. So the difference between the Dirac and the pseudo-Dirac case is that you have, for the pseudo-Dirac, you introduce some tiny Majorana mass, right?
yeah.
In the
I
so
basically this M is very tiny. Yes.
right. So, but how tiny? So it doesn't matter how tiny it is. Then you get this enhancement of 10 to the 11 or so.
I think it's so basically this condition has to be satisfied. I think it's also so basically there is a hierarchy, right? So mm square, this
Okay. So this
square has to be bigger than md squared times md over mu squared, right? Which an md over mu is very, very small, and that's squared. So I think it is just it's really hopeless at that point to get a
all right.
Majorana.
Yeah, but the effect of introducing this Majorana mass parameter is the same. Is the same on this sum of the PMNS combination of matrices that you had for the just the Majorana case, right? That is just that you don't have the linear or the non-proportional to mass term in the
Yeah, because
in the
it's
sum that you had in the
still
amplitudes.
these are still Majorana neutrinos. These are
Right.
still Majorana neutrinos. So we should not be thinking of them as Dirac, even though the name is pseudo Dirac. We should be still thinking of them as Majorana
Yeah.
neutrinos.
They're more like pseudo Majorana. Okay.
So the
All right.
thing, they don't call it pseudo Majorana because they are fully Majorana, but maybe little Dirac because the Dirac mass is bigger
Okay.
than the Majorana
All
mass.
right.
Yeah.
I make that a comment. I think that the point here is that you have as you mentioned, right, that you have the active and the sterile neutrinos, right, and they have very small mass splittings, right, and the mass splitting should be proportional to this m
Yes,
parameter.
the Majorana mass, which is small. Yeah.
Right. So what I think that leads to is to a cancellation, right, between the different contributions. That in the limit of having a zero mass splitting gives a precise cancellation, and then you get a Dirac pair, and then you get your first diagrams, right? It should be something like this, I
think
think.
so. Yeah.
Yeah. So since I have the mic on, let me ask another question. Sorry. So I was wondering also, once you go to a specific model, for instance, again with heavy neutrinos, sometimes you calculate the impact on the parameter space from neutrinoless double beta decay, and then lepton flavor violation and mu conversion and things like this. So I was wondering if you are aware of within a specific model, how does muon antimuonium conversion what's its impact on the parameter space compared to other searches like mu conversion or mu to 3 leptons and these kind of things?
That is I'm not sure of the top of my head, but yes, I know that mu e conversions.
Because those are not lepton-number violating, right? Those are only lepton flavor violating.
I think mu e conversions are in they are it's kind of the same operator, right? I think it's they're like complementary searches. The same operators can be probed for mu e operators as well as for mu e conversion as well.
If they change Lepton-number for sure,
Yeah.
for sure. But I don't know.
So it's a mu-e conversion. I think is a complementary probe to this. You still get access to this me. There is this me mu or mee times m mu mu that you have access to from there as well. But wait 1 second. Maybe mu-e conversion is me mu, which is different from this. This is mee times me mu mu mu, right?
Right.
Yeah. So this is mee times m mu mu, right?
Right, which are the number violating ones.
But
Yeah.
there's also other combinations of the PMNS matrix like me mu, which is different from how we defined it in this paper, which is it's literally just this number, but or actually something like this with ei mu I mi squared. So there's me mu as well. So maybe it's I have to think about this, but it could be proportional to a different combination of PMNS matrix elements.
I think that just violates lepton flavor, not number. Yeah. So you would.
This one violates the muonium antimuonium mixing. It does not violate total lepton number. Yes, that's right. But then E mu. Yeah, it could be. I have to sit down and draw the diagram. It could be proportional to some other combination of PMNS matrix elements.
Okay.
But it's a complementary probe. Yes, people have talked about this.
Okay.
All right. Thank you. I think that at this point we can stop the webinar. Thank you very much, Mijo, for being with us today, sharing your work, and thank you to all who watched live the streaming and those who will watch the streaming later in live. To all, this is a reminder that you can subscribe to our YouTube channel and social networks on X, Facebook, etc. And also the Google Groups mailing list so that you are always updated about any upcoming webinar. Our next webinar will be in 2 weeks. We hope to see you all, and let's stay in touch. Thank you all, and have a nice rest of the week. Okay, I think that the stream was